Hi everyone, and welcome to this webinar today with the HPA, NIC, EIC and NAPIT. So we're looking at heat pumps and RCD selection today. Just before we introduce you to the panel, a little bit of housekeeping, as Gary's just put in. As we run through the session, if you have any questions or comments, pop it where it says say something nice. There's also an ask a question button, which is a question mark with a speech bubble. So at any point, if you pop them in there, we can put those to the speakers, to the relevant people, as and when. So please feel free to comment as much as you like. So let's introduce you to our speakers today. We've got David Cowburn from the HPA. David, welcome. Can you tell us a little bit about your self and your role at the HPA, please?
So David Cowburn, I'm a technical consultant to the HPA.
Perfect. We've got, so we'll go in order of what I've got on my screen. Sam Donaghy. Sam, can you tell us a little bit about your role at the NICEIC, please?
Okay, so I'm Sam Donaghy from the NICEIC. Title is a bit prolific, Head of Technical Advice and Practice, but I'm really the team leader for the Technical Helpline and Technical Services team at NICEIC.
No, perfect. And we've got Steve Humphreys from NAPIT. Steve, can you tell us about your role at NAPIT, please?
Yeah, thanks, Joe. Good afternoon, everybody. Yeah, and just really glad to be part of this webinar on this subject. So, as mentioned, I'm Steve Humphreys. I'm the Technical Commercial Manager at NAPIT. I've been at NAPIT now for a couple of years, and my role is a bit similar to Sam's, really. I suppose we support our members with the wider technical team, a range of areas from electrical installation to renewable technologies. We do things like webinars like this one, podcasts, technical articles, books. And in between that, we do trade shows, installer show coming up. Looking forward to that one, Joe, and the rest of the team. And also we do other trade shows and deliver seminars on all a wide range of subjects. And and in between that, me and Sam both sit on various trade committees as well, and JPEL 64, which is responsible for the development and maintaining of the wiring regulations. So we do fun stuff, and also it's not always not so fun stuff, but yeah, it's a good role. Good to be part of it.
I didn't even have to pay you for the plug for Installer Show, so thank you, Steve. So in today's session, the HPA have published some guidance with NAPIT and NICEIC, the two largest registration bodies in the electrical sector, to provide certification for heat pump installation businesses. So Dave, what are we looking at in today's session? What's happened? Why is it important?
So I think the one thing to say here is the reason that we felt guidance was necessary was the sheer number of questions that were being asked in this area. And that's being driven by the fact that the rate of heat pump installation in the UK is rising rapidly. So in 2024, we sold just short of 100,000 heat pumps in the UK, which was set a new record for the UK. And 2025 to date is outstripping 2024. So we're seeing year on year growth in the sector. And what that results in is you have electricians and electrical contractors who are coming across heat pumps often for the first time. And they're asking questions, and they're coming at it from the end of understanding the regulations, the wiring regulations, but not necessarily having great knowledge about the technology. On the other side of the coin, because of the growth, we've got a lot of newly trained heat pump engineers. They may be heating engineers from other appliances, but new to heat pumps. And they're coming into the sector to meet the demand, and they're asking questions from the other end. They understand the technology. They don't necessarily have a strong understanding of the wiring regulations. And there is information all over the place. You've got a bit in the wiring regulations, but not specific to heat pumps. You've got manufacturers' instructions. You've got guidance from RCD manufacturers. So what we felt we could contribute here was some key questions and answers that were being raised around the selection of RCDs to try and give guidance in a manner that for those who aren't going to actually do the electrical work is informative. For those who are going to do electrical work, helpful and instructive in terms of signposting other information and things like that. So as you said, we've worked with NAPIT and NICEIC to develop the guidance. They're both HPA members. I'm very grateful for their work on this. But also in publishing it, we did send out the guidance to review to a wide range of stakeholders. So it had a long gestation period to get to its end product. A lot of people had input to it. for which we're very grateful. And it is free, so it's guidance that is free of charge. And as you see in the chat there, you can get it off the HPA website just by following that link. And obviously, we hope it's helpful, and we hope that today's webinar will shine a spotlight on the kind of issues that we're addressing.
Yeah, Sam, why was it important for you guys as NICEIC to get involved in this piece of work?
Yeah, pretty much as Dave said, we were getting calls. Heat pumps are one of those things where there's quite a crossover between the electrical industry and the heating and plumbing industry, because both sides are involved in a heat pump installation project. And so we were getting questions from both sides. So it was clear that there was some clarification required and some confusion, which we hoped to try and resolve with the guidance.
Yeah, Steve, is it similar to you? Is this something that you were getting quite a lot of, because you sit on the tech desk, don't you? Is this something that you were getting questions from both electricians and kind of traditional heating installers?
Yeah, definitely, Joe. We get a lot of calls into our tech helpline about weird and wonderful things, but RCDs is always a big one that comes in. I mean, you generally RCDs can be confusing for electricians and other technical trades anyway, without then associating them with heat pump installs, solar PV, whatever it may be. So, like Sam said, we need to get some clarity out there to our members and wider industry to make sure that we're making sure that installs are safe. That's the primary concern for any design and install consideration, that it's done safely and we don't have the issues we're going to talk about today.
Yeah, so we've got a slide coming up that goes through the 4 simple steps, but let's take it back to kind of the start of it. So what is an RCD? What is it for? How does it work? Who is the best person to answer that first question? If we go baby steps.
Okay. Traditionally, protective devices were built around a threshold. So if the current exceeded a threshold, then the protective device operated. So that's a fuse, a circuit breaker, and those protective devices operated on the basis that under normal certain conditions, the current required for normal operation would be below a threshold. If there were a fault, it might go above, and then those overcurrent protective devices would operate. But there are other types of faults which don't result in a large enough current to operate those overcurrent protective devices. And that's where an RCD has an advantage, in that it's looking at a difference. So RCD is residual current device, and it basically is looking to sense the difference between the outgoing current and the incoming current for the circuit. And when the circuit's operating under normal conditions without a fault, those two things should be the same. The circuit current that goes round will return. If there were a fault, and that can be for a number of different reasons, then there could be a small imbalance, and an RCD will then detect that imbalance and operate, whereas the overcurrent protective device wouldn't. So quite often these will work either in association with an overcurrent protective device or on their own to detect that difference, and effectively it sees that difference as a non-normal operation, a fault, and then it will operate when it detects that difference.
No, so Steve, are they there to protect people, equipment, both?
That's a good question, because sometimes we consider RCDs just for the protection of people when we think about prevention of an electric shock. And you could argue that that's the most common application and probably one of the most important applications to protect against electric shock. But there are times when we use RCDs, and they've been around for many, many years, that are used to protect equipment and maybe an electrical installation as a whole. So instead of being used for what we'd call additional protection, is where they are to protect against electric shock harmful to people, they can also be used for fault protection and also fire protection. So, under certain fault conditions, the protective measure, we could have insulation faults, for instance, where we could have an RCD in place for that. We could have fire hazards depending on the type of installation, agricultural or sort of farms where there's hay stored. That's a potential fire hazard. So if there's maybe an earth fault in those situations, then we could use RCDs as well. And also, without getting too complex, when we use different types of earthing systems, like a TT system, where we'd have an earth electrode, in those kind of systems, because we've got a higher resistance to earth than normal ground systems, TN systems, this makes it difficult enough for a fault to trigger that overcurrent protection. Like Sam talked about, normal fuses, normal circuit breakers. So in that instance, an RCD would be in place there as well. And it's just worth mentioning, lastly, when we say it's not an either or, it might be people, it might be equipment, the whole installation. It could be a combination on certain installations, larger installations, where you'd have lots of RCDs in place as well, to do all kinds of things to protect equipment and people at the same time.
Yeah, so Dave, when we're talking about heat pumps, why does RCD selection matter? Why is it so important in those installations?
Yeah, so I'm picking up on the comments from Steve and Sam there. Safety, the way that the RCD works, and whether it results in protection for consumers and individuals. The correct selection is important, and the reason for that is that most heat pumps, not all, but most heat pumps will have components that will produce different situations in terms of earth leakage. So frequency components different from the 50 hertz that we're used to in the normal supply, direct current components, all mixed up in a signal, and therefore picking an RCD that will actually work correctly is really important. And from the heat pump point of view, if we are going to achieve the targets that we need to in terms of deployment of heat pumps, consumers have to know that they're safe, as you would expect with any electrical appliance, but also they have to know that they can rely on their heating system. So there are two things that can go wrong if you make the selection incorrectly. One is that it fails to trip when it should, which is then that risk to safety, personal safety. But the other side of the coin is tripping when they shouldn't, and then your heating system goes off when it shouldn't have gone off. So I think I'll hand over to technical colleagues to explain what causes those things, but that's why selecting the right RCD is really critical.
Who fancies explaining tripping to us?
I think I can talk about some of the dangers around definitely blinding of RCDs, which is something that is not new. It's been around for a while, and it's really important, like Dave just mentioned, that this selection is so important because things like this can happen. So in a simple terms, RCD blinding is an incident that occurs when the RCD is saturated by DC current or sometimes exposed to high frequency waveforms. And this is going to prevent it, like Dave just said, from operating under fault conditions, or can reduce its sensitivity. So the RCD is not acting like it should do. Now, the danger is that if the DC blinds the magnetic core of the RCD, so when Sam talked about imbalance, it's running through a core, and that balance might not be detected if the RCD is blinded. So again, in simple terms, its ability to detect faults is compromised due to that saturated magnetic core. And as we know, the characteristics of heat pumps, inbuilt inverters, the drives, they're sensitive already, and this sensitivity of an RCD installed upstream could cause these problems. So it's important that, like, the designer or the installer selects that correct type of RCD, especially if there's upstream RCDs, and obviously the one protecting the heat pump. So the RCD at the origin that is required for the heat pump will need to be at least the same type. And obviously we're not going to get into selectivity too much, but there are articles out there that have been released that look at that in detail with good drawings that will show you almost like a line diagram of where the RCD should be in place to stop this blinding occurring.
Yes, and what about nuisance tripping?
Yeah, just to add to what Dave and Steve have said, nuisance tripping can occur if you do select the wrong type of RCD for the application, and that can obviously be frustrating to to the end users, let alone the designers and installers. And that comes in two forms. So firstly, each RCD has a nominal rating. So it's looking for an imbalance or a difference based on that nominal rating, whether that be 30 milliamps, 100 milliamps, 300 milliamps, 500 milliamps. And the reason for different ratings are because different items of equipment, different circumstances can generate that imbalance under normal operation, so not due to a fault. The obvious example is IT equipment, for example, runs with a small leakage current. And so if you put the wrong size RCD on that IT equipment, it will result in the RCD tripping, even though there's no fault. It's normal operation. So that's one way that you've got to ensure that you select the right rating. And then the second way is that it's become apparent over time as RCDs have developed that there is also an element of DC leakage within AC and DC circuits. So some AC products and equipment produce DC leakage current, which can have the blinding effect that Steve talked about. And so in more recent times, sort of the second generation of RCDs have been designed and manufactured to still operate even though there is an element of DC leakage current about. Now, they will again have different ratings, which is where we get the different types of RCDs. So type AC was the original, and then to have devices that are DC tolerant, we've developed type A's, B's and F's. Now those devices will tolerate different levels of DC current and still operate correctly. So those are the two elements of blinding. First of all, make sure that you select the RCD with the correct nominal rating so that it's not going to trip under normal circumstances. And secondly, also select the RCD that operates correctly with the DC leakage current, which is there under normal circumstances. If you don't do either of those selections, then it can result in nuisance tripping, which means your RCD will trip when it's normal circumstances, and you're going to lose supply, which in the case of our heat pump means we're going to lose that heat generation, and if we've got a backup, unless we've got a backup system, then there's going to be no hot water within the installation.
Yeah, so it's like with many things, it's just about proper design and selecting the right product for the right application, which is what we're all kind of that's what everyone's trying to do. So we've got to select the right RCD for the application. We've got these 4 steps, which is in the guide. So Dave, step 1, manufacturer's instructions. Talk us through that one.
So it's always with any installation. Most people putting in equipment in are going to be following manufacturer's instructions. That's your normal starting point for what you're going to do. The thing that would draw attention to here is the statement that we recommend that manufacturer's specifications are followed, and the question will then come back at us, and has come back at us, why isn't it mandatory to follow manufacturer's instructions? So I'm going to pick up on that a little bit. One reason, of course, is that houses are different, buildings are different, and the manufacturer themselves can't know the electrical installation onto which a heat pump is going to be installed, and can't account for every single variable within that. That becomes the job of the installer and the electrician, for example. So you need to think about more than just blindly following instructions sometimes, but also it's sometimes the case that manufacturer's instructions are not as specific as you might expect them to be. Partly that comes from heat pumps being international products. So manufacturers will make a product for the whole of Europe or beyond, and will put a statement in their manufacturing instructions saying follow local wiring regulations. So then you have wiring regulations say take account of manufacturer's instructions, and manufacturer's instructions saying take account of the wiring regulations, and you still haven't got an answer. Potentially, that's a potential situation. Or they might say fit a suitable RCD, and then it still comes back to the designer to make that selection. Others, on the other hand, are very, very specific. So you'll pick up a particular heat pump manufacturer that's done a lot of research on their product and its application in the UK, and they say you should fit a particular RCD. They may say it in a very specific way that you must, or they may say strongly consider, or whatever. But so you've got those. And then the third possibility, and there are some on the market still, is where the manufacturer's instructions say nothing at all. And therefore, again, it comes back to looking at what the appropriate decision is outside of it. So it would be great to be able to say, just follow manufacturer's instructions, we don't need to produce any more guidance. But the fact is there's a bit more to it than that, as I'm sure we'll carry on discussing.
Yeah, Sam, what do the wiring regs say about MIs?
Yeah, so BS 7671, the wiring regs, which covers the requirements for electrical installations, it actually is worded such that the installation of electrical equipment shall take account of manufacturer's instructions. Now, that's for a number of reasons. As Dave said, because sometimes manufacturer's instructions aren't as detailed as are required for the electrical installation side. And there's also situations where the manufacturer's instructions are sometimes behind wiring regs because they were written a long time ago, and sometimes they're ahead of wiring regs because BS 7671 also goes through cycles. So it's because that BS 7671, the wiring regs, are there to cover all the specified types of electrical installations. It's not specific to heat pumps, which is why it says take account of manufacturer's instructions. I can think off the top of my head of an example of another piece of equipment which still talks about protect with a fuse. Now, there's no need for it to be protected with a fuse because there are better types of protective devices now. So sometimes the regulations have leapfrogged manufacturer's instructions, and sometimes manufacturer's instructions have leapfrogged the regulations because they're both cyclic and they're not actually totally in sync and combined. So that's why it's a generic statement, and the generic statement is take account of manufacturer's instructions, but it's still down to the designer of the electrical installation to follow and comply with 7671 for the electrical installation aspect.
Yeah, Steve, Sam mentioned it then. I think you mentioned it earlier on in the webinar as well. What does the wiring reg say specifically about heat pumps and RCDs?
It's a good question. Nothing is the only answer.
Yeah.
No, well, it says nothing, but it's how you interpret the reg. So it is correct that BS 7671, the wiring regulations, it has nothing specific about the installation of RCDs for additional protection as regards for a circuit supplying a heat pump. That is actually true. So when we have additional requirements, those are intended for socket outlets, mobile equipment for use outdoors, and heat pumps don't apply in those circumstances. However, we do look at then selection of an RCD for a heat pump allows for other equipment, and that is covered in the current regulations. So the most likely requirement to install an RCD is because of the type or installation method, so the cable that's being used to supply the actual heat pump. Now that falls under the regulation group 522.6, and device selection is covered also in part 5, which is 531.3. So there are references, but it's not specific to RCDs for heat pumps. So there is actually a product safety standard, which is BSEN 60335-240. Now that covers RCD selection for heat pumps in quite a bit of detail, and air conditioning units and other things. But it's worth noting that is a product standard rather than an installation standard. And we're in a world now, I think Sam will agree, where sometimes the product standards cross over into ISO standards and installation standards cross over into product standards. But we've got to be clear that, like we've just said, there is nothing specific in the wiring regulations that relates. That product standard does say that appliances accessible to the public for installations of an RCD should have a rated current of not exceeding 30 milliamps, and it uses the word advisable. Okay, so it doesn't say must, and it's not a you shall, it is advisable. So that's what's in the product standard. And then for appliances that are not accessible to the public, so it could be fenced off in somewhere where the public can't get to it, it says that the residual current operated should be specified for the manufacturer, which we've just talked about isn't always black and white. I mean, I'm going backwards a bit here, but how many times have we opened some manufacturer's instructions and not understood what it actually means? Normally something I've got from IKEA or other stores that are available, but you know what I'm getting at. And remember with heat pumps made for a global market, it's not always clear that they're going to comply with UK regulations. So like Sam said, the regulations are always being updated, but we can't bring in everything related to every bit of equipment. Otherwise, it's already a big book. It's going to be 4 times the size of what it is now, and we're going to end up with a product standard in an installation standard. So by following part 5 of those certain things, like I said, with the weight, the cable that's wiring it, that will be specific to the actual supply to the heat pump.
No, it's interesting. So step 2 is to check if an RCD is required. So does that suggest that it's possible that an RCD might not be required in some circumstances?
Very nice segue there, Joe, into the next section. It's like we've done this before.
I know.
Yeah, in that group of regulations, which is 522.6.204, which is a UK regulation, anything ending in a 200 number is specific to the UK. There are some circumstances where a circuit supplying a heat pump may not need RCD protection. Now, like I just said earlier, and that might be required depending on how the cable and the wiring system is installed. Now, the methods described in that regulation talk about protecting cables that were installed in walls or partitions that might accidentally be drilled or someone screw into them. You know, I used to get this all the time when I was an installation electrician. Someone call you out, oh, something's tripped. You know, someone's got a nice picture that the wife's asked the husband to hang up and then suddenly gone through a cable and tripped it. So, you know, we sort of say that if the cable can be buried more 50 mil or more into a wall, then, you know, it's normally okay. But that's not really, you know, doable in most circumstances. So where the cables in the circuit have mechanical protection from screws, so let's say it is buried deeper than 50 mil, or it's got earth metal armor, an SWA cable, it's put in metal conduit or metallic trunking, it could allow the designer to negate the need for an RCD in those circumstances. So although I just read out that product standard that said it's advisable, this is sort of not the get out of jail card, because that's the wrong term to use, but this is the reason where sometimes it's not always necessary. And we do this quite a lot of it in solar PV. We do talks where we recommend if you could design out, excuse me, an RCD because of things like the nuisance tripping, the blinding we've just talked about, then there might be circumstances where you can. So in some circumstances, perhaps where the cable supplying the heat pump is on the surface of the wall, could be clipped to the external wall rather than embedded in any fabric of the building. This could be another reason where an RCD is not required. But then we've got the other side of the coin where we say, however, manufacturer's instructions must be taken into account. So, you know, we're in a weird world where on one hand we can say that it might not be needed, but this is where the designer and the installer's got to look at the whole picture and say, is the manufacturer's instructions talking sense? Does it comply with what we've just talked about in BS 7671? And is the actual installation, the design, when I've done a survey, that maybe negate the need for an RCD? So there are circumstances where they might not be needed.
Yeah, so are there any particular ones that come to mind about where you could design out an RCD, like new build properties or things like that?
Yeah, it depends, because like I say, you know, we're seeing a lot of new builds now will automatically go for fitting some kind of renewable technologies, whether it's solar, battery storage, or heat pumps as a matter of course. You know, when we know, like Dave talked about, the government targets are very ambitious to achieve that. But new builds, it's looking at that then where the designer or the project managers of those kinds of installations is thinking out the box a little bit and doing some of the things I talked about, routing the cables sensibly. What is it actually wired in? Is it mechanically protected? And another point worth raising, I don't want to cause more confusion, is what is mechanical protection these days? Impact drivers and drills that are strong these days, will go through a knife through butter, literally as much through a wall and a cable. So we've got to start thinking, can we negate that? So new builds could be an answer depending on the design. And also with retrofit, I would as an installer and a designer be thinking, right, where am I routing this cable? What's the best option? And it might just be that I do need an RCD at the end of it. So it is looking in the round at the whole picture rather than isolated incidents.
But then, Dave, if you go against the MIs, or if you do something that, if the MIs are quite broad, what could then come down the road for you as an installer?
I think the key point is the one that was made earlier about the wiring regulations say take them into account. So if you are trying to design out the need for an RCD, then you are taking responsibility for your design decisions, and that may be perfectly correct. But you have to be conscious that you might have to justify the decisions you've made and that you are making the correct choices. There's a liability risk if you get it wrong, obviously, and that's what insurance is for. But the final point really is whether there is any risk that you might have an impact on product warranty, for example, or even insurance-backed guarantees. So most heat pumps are installed under things like the microgeneration certification scheme or boiler upgrade scheme, or the building regulations where they're self-certified. And every single one of those schemes requires an insurance-backed guarantee of the installation. What you really don't want is some small print within that guarantee to say failure to follow manufacturer's guarantee negates this policy. So they may not say that. I'm not saying that they do, but be careful. My advice would be check with the manufacturer or with the wording of their warranties and guarantees, and make sure that if you deviate from manufacturer's instructions, you're not running any risks in that area. And of course, just to go back to the point that we made earlier about manufacturer's instructions often say things very differently from one to another. One manufacturer may just say do X. Another manufacturer might say, well, do X if an RCD is required, leaving the door open to the circumstances that we've just been talking about where it might not be required. In which case you are following manufacturer's instructions.
Yeah, you can see why you guys have made this guidance to kind of help with these potential grey areas. So on there, we've got steps 3 and 4, which cover selecting the RCD type from the manufacturer's instructions or information obtained by contacting the manufacturer. So can we describe the types of RCDs that can be under consideration?
Okay, I'll. So originally, when RCDs first appeared in the general market, they were a type AC. And their operation was based around standard residual sinusoidal AC alternating currents, and didn't take into effect any other possibilities. So those were our first type of ACDs which we saw starting to appear in electrical installations. More recently, we then, because of the knowledge that those RCDs can be blinded with DC currents that are imposed on the AC signal, there have been developments to make RCDs which will still function. So they don't block the DC current, and that's something important to consider, but they tolerate it and will still operate correctly. So we have then got a type A RCD, which works the same as the original type AC in that it's for residual sinusoidal current, but also operates correctly with residual pulsating DC currents up to a maximum of 6 milliamp. So if we've got a 6 milliamp maximum DC current superimposed on the AC, our type A's will still work. Over 6 milliamps, then we've got type B's. So a type B will do everything that a type A does, and therefore everything that a type AC does, but will then tolerate those DC currents up to 10 milliamps. And then we also then need to consider the frequency. So type B's, a standard type B has to be able to cope with frequencies up to 1,000 hertz, 1 kilohertz, and that's how a B will differentiate from an A. So greater current tolerance and higher frequency. And then we've also got F, which again, similar to an A for frequencies, and also up to that DC current limit of 10 milliamps. So this is where we talked about earlier, deciding what level of threshold am I thinking about in terms of DC, because that will, and what frequency, and that will lead us into determining whether we require an A, an F, or a B. Now, those are the only ones that are recognised currently by BS 7671. But as we know, there's a cyclic thing, and manufacturers are working on other devices because we know that sometimes people are being made aware of appliances and products that produce greater DC values, higher frequency. So there may be further developments. But currently, we have the old traditional style AC. We've then got AFs and Bs, which tolerate DC and still operate correctly at different levels and at different frequencies.
Nice, and then that's what that slide pertains to as well. So Steve, what does the guide mean by using details of electrical characteristics and table 1?
Yeah, on first glance, if you get to sort of step 3, it seems like we're getting into the realms of, like, it seems a bit scary, but the guidance that's in the HPA document is very clear, and especially in table 1. So what we're saying with this one, if the manufacturing instruction do not specify a particular type of RCD, which Sam's just covered, then that gives us, we've got to determine the electrical characteristics again, which Sam just alluded to. So what is the DC coming back, and what levels, and what is it pulsating? Is it smooth? Which again can seem a bit tricky. But on table A starts with, like Sam mentioned, those the type A RCD, and it then gives you those clear tolerances, the pulsating DC currents. So I'm not going to go over those again because Sam's covered them. But what we've got to realise is the difference there is because some heat pumps will work perfectly okay with a type A, that and some manufacturing instructions will say that, because they're going to end up with sort of equipment that hasn't got those complex inverters or drives or electronics that's going in that particular system. So if we're dealing with normal pulsating DC residual currents, that is just what we know as half rectified DC, often described as pulsating. So it's current that's flowing in one direction and it's got periodic pulses. Typically, like, we find this quite commonly in a lot of electronic equipment, washing machines, simple power suppliers, basic rectifiers will all have this simple DC current. When we talk about, and Sam mentioned, that composite residual currents, which are more suited to obviously the type F and the type Bs, this is dealing with different types, a combination of AC residual currents, pulsating DC currents, smooth DC currents, and mixed frequency components. So we've got higher harmonics in it. And as our electrical equipment gets more and more complicated, this is why type Bs and type Fs are becoming more and more common. We've already looked at type ACs now, a sort of, we don't use them anymore because we haven't got standard resistive loads. Because we've got the DC components, they're gonna trip all day long as soon as look at them funny. Whereas your A's, your F's, and your B's have got that more tolerance. So they commonly arise in installations with variable speed drives. UPS systems use them a lot. EV chargers are more common. Photovoltaic inverters, all these kind of produce multiple residual currents simultaneously. Now, what we found in table A is that you've got the supply characteristics that will match that type of RCD. But if you look in it as well, it's also got those further notes. So those further notes are going to give you also a clue into what's going on. Now, the manufacturer's instructions might not have that, but they'll have data sheets, and that's important. So if you're using, a reputable heat pump manufacturer, they'll have those data sheets, or pick up the phone, drop them an email and say to them, I need more information about the supply characteristics of your inverter. And like Dave's already mentioned, they'll all be different. That some will tell you one thing, some will tell you the other. We're going to come on to a little bit about that later, but it's important that you know the supply characteristics. That's going to inform the designer's decision for what RCD to use. So table 1 is very important for that particular step.
And Sam, why is it categorically stated that type AC can't be used?
So again, our British standard for the electrical installation aspect has got a regulation which clearly states that type AC RCDs shall only be used to serve fixed equipment where it is known that the load current contains no DC components. So as Steve said, because of the equipment within the heat pump, particularly things like inverter drives, but generally any electronic controls, that will introduce a DC element into the installation. So we definitely can't say that it's known that no DC component will be produced. So that means that ACs definitely can't be used unless, and I don't think it would be possible, you got a statement from your heat pump manufacturer to state that there would be no DC components produced by the item of equipment.
Nice. And then, Steve, why isn't it a blanket advice to fit type Bs?
Yeah, I think on first glance, that might seem like a really good solution. We know type Bs are sort of the big boy of the industry, for want of a better word. It's an all-in-one, it covers all angles. So, why wouldn't we go for a type B? But we still need to be careful as designers and installers when we select it. We've got to get the right type of protective device for the right type of installation in any installation, not just heat pumps. So it's even more important with heat pumps being installed. Now, we've already said, and we've said this time and time again, this could be as simple as following manufacturer's instructions, as mentioned earlier. Could you then be saying the warranties, the small print that Dave mentioned, you're going against that, and some of the warranties not valid anymore. And another reason is that many heat pumps, as I just said, do not produce smooth DC residual current anyway. So a standard heat pump with single phase compressors, without that complex electronics I talked about, might only generate AC or pulsating DC. So in that case, we have seen heat pumps where a type A will be absolutely fine. As they become more modern, more complex, better, more efficient, we're seeing more of those electronics and drives that are becoming more complex. So, there might be historic reasons for that. Some type Fs that detect mixed frequency may also be suitable for certain kinds of heat pump inverters. Again, manufacturer's instructions. And that is why the characteristics we talked about in table 1 are so important. And another reason is that type Bs, if you just go for a blanket approach to type Bs, they are more susceptible to nuisance tripping. So although they're the daddy of the thing, due to their complex electronics and sensitivity to harmonics, maybe some interference, in some circumstances where DC leakage is not present, they could trip. So if you put a type B in, you could actually be causing yourself more of a problem. So, and another reason, which obviously we're talking about safety and we're talking about proper design, we wouldn't be doing the right thing for installers as it's an installer show webinar if we didn't talk about the economic reason. Type B RCDs can be much more expensive, sometimes 5 to 10 higher than type A's. So actually, you think about the cost implication for a customer, which shouldn't be your first consideration. I do want to stress that. But for an installer, that is a consideration, and certainly for a customer. So where a type B is not needed, not only for the reasons I've just explained, it could be just it's an expensive bit of kit that you didn't need to install.
Steve, just down on you, because we've had a question about type Bs from Chris. Are we saying that BS 7671 doesn't recognise type Bs?
We're not saying that at all, no. BSM 671 recognises all of the devices that are on the screen now that Sam went through. AC, A, F, and Bs. So those are British and European norms that are recognised by the standard.
No, perfect. And then Dave, coming to you, what do you choose if there's nothing to support your choice?
Okay, so I'm just going to carry on with the last the question that Chris has asked in the chat, and one of the things we get asked is about Type B plus. Now, Type B plus has come onto the market from Germany and is produced to a German standard, which isn't it hasn't been tested or approved against any European normalized standards. So it's being talked about a lot as a possible RCD for heat pumps, but that one isn't recognised within BS 7671. So that's what. Oh, in fact, that's what the chat's just popped up as well. Somebody else making the same statement. So Type B plus is not recognised within BS 7671, nor is it tested to product standards that are recognised within the UK at the moment. So just to clear that one up. Going back to the question about when there is nothing to support a choice. Now, hopefully that shouldn't be the case. So we put together the steps of guidance specifically in order to find the answer to the question about what RCD you should fit. And therefore it should be a very unusual situation that brings you back to the point where there is no advice at all. But let's assume theoretically if that is the case. So we know that Type A's often cannot reliably detect faults with the kind of frequencies and DC components that we've talked about where there are inverters. So I'd probably, if I had nothing else to go on, I would probably rule out Type A. I'd have to think about whether the heat pump had inverters at all. So for example, air source heat pumps rely on ambient air temperatures which vary quite a lot, whereas a ground source or a water source, the source temperature of the heat pump itself is more stable. And there are ground source heat pumps in particular on the marketplace that use fixed speed on-off rather than inverters and variable speed. So think about that a little bit. That leaves you with thinking about Type F and Type B, and it's strange that it's not in alphabetical order, but F, so B is kind of spec'd above F. The question I would ask myself is, can I guarantee that the characteristics that RCD is exposed to will result in the effective operation of a Type F? If I can, then a Type F is probably fine. If I can't, then I should go for Type B. Now, that does mean, and the reason for that is we're literally, the scenario we're talking about is no other information is there to support our choice. So we're recommending Type B at that point because it protects the broadest range of characteristics available within the set of RCD types that we're talking about. And even in our guidance, we say, but this does represent the most expensive option out of these particular types of RCD. But let's put that in context of the price of a heat pump. So, 4 or 5 times more than the cheapest RCD is still a percent, 1% of the cost of a heat pump installation, in a nutshell. So, as part of the overall cost of what you're trying to achieve, the RCD shouldn't be, it shouldn't be considered a major cost of component of the costs.
Plus the BUS grant as well, which helps with things like that, doesn't it? Because you're getting the £7,500 off the installation.
Very true.
Joe, sticking on selection, Joe has asked, some heat pump manufacturers ask for Type C, which is not listed here. Why is this? Who fancies?
C. I feel like we're perhaps in a world of things that don't exist there. Maybe the confusion there would be not necessarily the type of
RCD, but the
RCD
type of
characteristics.
Yeah.
So there's 2 things going on here, and it does cause confusion again amongst electricians, and never mind other technical trades such as heating engineers, because what we're talking about here with these types that's on the screen now is obviously we're talking about the current characteristics for the type of RCD or you know, what it does, its operational side, dealing with things like pulsating current and the rest of it, up to 6 milliamps, 10 milliamps, and the rest of it. When we talk about type Bs, Cs, and Ds, we're talking about the curve characteristics for sort of, if you think of circuit breakers, they'll have a B type, which mostly used in domestic settings. In my day, Cs were then used for things like motors and Ds. So as things got more complicated, you know, in big industrial jobs, you would put type Ds in because we're talking about high inductive loads starting up and maybe tripping that circuit breaker. So we've got to be careful when we talk about what this webinar is about, and the different types we're talking about here is definitely just about the rated current that these things deal with. So yeah, not to be confused with types. When we call them types, it's not good, is it, Sam, that it's the same thing really? But
yeah. I think if we were starting again, we'd suggest using numbers for the RCD type to differentiate it from the letters for the circuit breaker type. But we're not at the start, unfortunately.
Like you said, if there was, please do.
Yeah, so just to finish the story on type B plus, one of the comments in the chat there is about type B HP. So there is a product on the marketplace which is marked HP for heat pump, and just to be clear, that is not a B plus. So the type B HP, which is branding from a particular manufacturer, that is a type B as recognised in BS 7671. So that has been tested and approved against UK product standard and is in line with BS 7671. But the HP is their indication that it's been specified for heat pumps.
Yeah.
No, perfect. We will. If you guys do have any other questions, we'll pop them in the chat because we've got about 10 minutes left. So now's the kind of time to do it. So any more questions or comments? Was there something you were going to answer, Steve?
No, it's just great that question's come in, because we know we're going to get this a lot on our technical helplines and maybe causing some confusion between the B plus, the one that's been made for the German market, and the BHP. And Dave's quite right. The type BHP is a type B, although the marketing of it looks like it's separate. It's not outside of BS 7671. It is a normal type B, and the way that's been done, so it's not like a B plus, is it's been manufactured, or sorry, engineered would probably be the better word, where they haven't altered any of the actual electronics, the way it works, to make it a new product standard. They've been very clever. What they've done is they've just, the component parts and the quality within them component parts as able to increase those certain characteristics. So, you know, the frequencies, it can get to a range of greater than 20 kilohertz. So that's the way that particular manufacturer has got over that. So they've not made it into something else. It's not a B plus, it is a B. But it looks like from the marketing that it might be something separate, but to clear that up, it's not. It is a B. It's just, let's say, what's the word you could use, an enhanced B, but it's, like I say, it's been manufactured or engineered to a high standard.
And I suppose if there is any of these questions that come up, like you said, like Sam's mentioned, products get released quicker than potentially regulations at points. So if you do have these questions, like, it is best to ask the manufacturer or ask you guys, essentially, isn't it, as the kind of tech experts at NAPIT and NICEIC?
Yeah, absolutely. You know, go back to the product manufacturer and get them to confirm that it does comply with all the product requirements of a type B. And as Steve said, it's got enhanced features, which then allows it to offer others. But so long as the manufacturer confirms that yes, it complies with type B, then you know, that's the information that you need to use to say that yes, it's a product that's specified and in 7671 currently.
We had another question come in, which we'll address as well. Hughes asked, is there a good reason why you would want to design out an RCD? It was something that Steve kind of touched on earlier, so we'll go to you for that one, Steve.
Yeah, the reason we would suggest designing out is because of some of the things we've talked about. When we've got complex electronics and inverter drives and high frequencies and residual currents, we're trying to stop this unwanted tripping or this nuisance tripping. Now, RCDs these days are a lot better than they used to be. You know, me and Sam remember the days when you only had to give them a glance and the trip. They were, but they've improved so much now when we've got these different types that we've talked about. But at the end of the day, it's still got the potential to nuisance trip. And if that perhaps was on, let's say, a split load board, an old RCD split load board, that could cause issues for the rest of your circuits, which is not great. We've not only turned the heating off or the hot water into a property, we've also maybe got rid of sockets, lighting, and whatever else is in that domestic property. So if there is a reason to design it out and all the angles we covered there with the wiring system and everything, then why not? Like I said, we do it in solar PV because of the same instances with inverters and other electronic equipment involved in solar PV installations that may have batteries as well. Then there's no reason why we can't necessarily do this for heat pumps. And again, I know we keep stressing this, but I would say if a manufacturer's instructions come, and we need to speak to the manufacturers more and more, if a manufacturer is specifying a type of RCD and you as a designer has looked at that installation and said, well, actually the supply to that I can get on an external wall, there's no way that cable's ever going to get damaged or penetrated by a screw, call the manufacturer and ask for the rationale why they're asking for an RCD. You might not get through to a technical team, I'm going to be honest, but actually with the decent manufacturers, the big players in the game, they will have technical people that will explain the reason why they are recommending an RCD is installed.
Yeah, Dave, because like you said, there's wiring regulations, there's manufacturers' instructions, but then when you go through the door for that property, then it's on you to kind of make the best decisions. And if anything does go wrong, or if there's anything, that essentially sits with the installer, doesn't it?
It does, and you're always protected by following guidance. So it's a similar thing with approved documents under the building regulations. They're not mandatory, but deviating from them makes you responsible for meeting the regulation itself. Whereas if you follow the guidance, then somebody else has made the decision as to what is an appropriate approach under the building regulations. And it's similar here with manufacturers guidance. And a manufacturer might have very good reasons for specifying a particular characteristic. So, for example, in the BEMA guide to heat pumps, which is much broader than guidance for heat pumps, and there's a link to it within the HPA guidance for anyone who wants to get into a much more detailed understanding of RCDs, there's a phrase against heat pumps which says that a type B RCD with a specific characteristic suited to the appliance might be required for certain heat pump types, and that's an allusion to this type B HP enhanced type B, because that manufacturer or those manufacturers who specify it have looked at the frequencies occurring within their appliances, and they've come up with a very specific characteristic where they recognize that it's not any type B, it's this particular type B that they want to specify, and that's why BEMA have added that to their guidance. But yeah, so there's that going on. And again, just to pick up on a question while we're on types about availability, we talked about cost. Another comment that's often made is that they're not very readily available. That's changed significantly in the last few months, and it is pretty simple and straightforward to get hold of a type F or a type B at a reasonable price within the context of a heat pump project.
And then, like you said, I'll pop the link in there again to the guidance that we put at the top. But Dave, your advice for people who have questions, for people where there might be confusion or they might ask all these questions like they did, is what are you saying now as the HPA? There's the resource. What else can they do to kind of make sure that what they're fitting is correct?
So you've got the HPA guide. It signposts other places that you can go and look, like the BEMA guide. So the BEMA guidance is very, very thorough. We're trying to answer some key questions. They're trying to provide information in a great deal of detail. But if you're not a qualified, competent electrical individual, then rely on using a competent, qualified electrical individual. So you've got two people sitting here who run the two largest registration bodies for electrical contractors. There are thousands of people out there that are qualified to make these decisions. If you're not one of those people, get advice from one of them, or as we've said a number of times on this call, do ask the manufacturers.
No, perfect. We will round off there because we're literally coming up to the hour. But thank you everyone for your questions and comments. We can answer other stuff in the chat as well. If you've got anything else burning, we can get back to you via there. There's some more information about, I've dropped the links in for the guidance, but about NICEIC, HPA and NAPIT. We are delighted that you're all joining us for Installer Show in however many terrifyingly few days, in 2 weeks time at the NEC. So if you haven't registered, tickets are free. All the content is free. Steve's doing tech talks. Sam's doing tech talks. They're all on panels and all that sort of stuff. HPA are very much involved as well. A lot of these manufacturers for heat pumps and RCDs are there, so you can ask them questions themselves. So you can register for free at installershow.com. See you all there. Thank you everyone for your yes, one more. This is available to watch on demand. So as soon as you finish, it turns into like a YouTube playback button, so you can fast forward, rewind. You can also forward it over to any friends or colleagues that might feel like they'd be interested in it as well. So yeah, thank you everyone for your time today, and thank you to the panel for your presentation and your answering of questions.
Thank you, Joe, and thank you everybody who's joined.
Yeah, thank you all.